As you receive this broadcast, an extraordinary event is unfolding within our solar system. Since the initial detection of 3I Atlas in July, celestial anomalies have become increasingly frequent. This ancient traveler from beyond our star system has perplexed scientists from the outset. However, its peculiar composition and faint green luminescence are no longer the most astonishing aspects. The true enigma lies in what has followed in its wake. Our usually tranquil cosmic environment has transformed into a bustling thoroughfare of celestial bodies converging with statistically improbable clustering patterns. From a synchronized arrival of 7 comets to a recent procession of asteroids passing Earth, the spectacle in our night sky is far from ordinary. Consequently, astronomers are compelled to confront a crucial question. What precisely is 3I Atlas doing to our solar system? Accompany me on this nocturnal investigation as we endeavor to ascertain whether we are observing a cosmic coincidence of immense proportions or a phenomenon far more significant. Part 1. An asteroid barrage approaches. Mid-September of 2025 was anticipated to be uneventful. Merely another period of standard celestial movement, the kind that scientists meticulously document before shifting their focus. Yet the cosmos had a different agenda. What transpired during those crisp autumn weeks was a singular event, a celestial procession that prompted scientists to urgently consult their telescopes and the public to ponder whether they were witnessing something beyond mere chance. The principal attraction made its appearance first, asteroid 2025 FA22, a colossal rocky mass measuring somewhere between 130 and 290 meters in diameter. On September 18th, it traversed past Earth at a distance just exceeding 2 lunar distances, approximately 835,000 kilometers away. Close enough to generate news, yet distant enough to allow for peaceful slumber. However, this is where the narrative intensifies. FA22 did not arrive unaccompanied. This was not the typical solitary asteroid making its scheduled appearance. Instead, it felt akin to an opening night at a cosmic theater, with multiple performers gracing the stage in quick succession. The diminutive near-Earth object, 2025 RJ2, had already made its entrance 3 days prior on September 15th, whizzing by at a mere 0.78 lunar distances, a mere 300,000 kilometers from our planet. In astronomical terms, this is practically a greeting. But these were not isolated occurrences. Throughout that same week, dozens of additional celestial bodies, passing at sub-lunar distances, traced their paths across our local celestial vicinity. Each one was meticulously catalogued and tracked by the global network of space surveillance systems. By the numbers, it appeared to be routine traffic, yet the clustering exhibited an unusual character. The timing seemed almost orchestrated, as if these ancient voyagers had synchronized their arrival for maximum dramatic impact. Subsequently, the supporting cast emerged. Comet C2025-R2, identified by the SWAN instrument aboard the SOHO spacecraft on September 11th, began to intensify in brightness, approaching naked-eye visibility near the constellation Virgo. Its tail stretched across the evening firmament like a cosmic brushstroke, discernible to anyone who knew where to look as twilight yielded to darkness. The comet's trajectory beyond perihelion remained uncertain. Numerous such objects fragment under the intense solar radiation, leaving behind only luminous trails of debris as testaments to their brief celestial existences. Concurrently, a familiar entity loomed in the background of every astronomical report. Apophis, officially designated 99,942 Apophis. This is the asteroid that once topped every planetary defense concern list. The 400-meter-wide rocky mass is slated for an uncomfortably close encounter with Earth on April 13th, 2029. That close passage will bring Apophis within 32,000 kilometers of our planet's surface, closer than our geostationary satellites. It will be visible to the naked eye as it streaks across the night sky at 50,000 kilometers per hour. Nevertheless, the true luminary of this celestial spectacle was still poised in anticipation. Concealed within the routine discovery announcements was something unprecedented. 3I Atlas, also recognized as C2025N1, discovered on July 1, 2025 by the Atlas survey team in Chile. This object stood apart from all others that crowded our telescopes that September. It was not merely another asteroid or comet from our immediate solar system. This was something far more extraordinary, an interstellar visitor, only the third ever confirmed, possessing chemical signatures that challenged fundamental understandings of planetary formation. The Atlas team initially detected it as an indistinct speck traversing the stellar field. However, as subsequent observations refined its trajectory, the calculations revealed an astonishing narrative. This object was navigating a hyperbolic path, indicating it possessed ample velocity to completely escape the Sun's gravitational influence. It originated from another stellar system, possibly light years away, and after its brief transit through our solar neighborhood, it would continue its journey into the cosmic void, never to return. What further elevated 3I Atlas's significance was its temporal alignment. Its closest approach to the Sun, perihelion, was scheduled for late October 2025, mere weeks after the September asteroid procession. Then, much like a performer exiting the stage, it would vanish into the solar glare, obscured by the overwhelming brilliance of our star. Nevertheless, persistence would be rewarded. In early December, as Earth's orbital motion brought us to a more advantageous viewing angle, 3I Atlas would re-emerge from behind the Sun's radiant curtain, providing telescopes with their prime opportunity to scrutinize an authentic fragment of interstellar matter. The observational window was impeccable. Perhaps too impeccable, some might suggest. At its closest proximity in December, the object would still be 1.8 astronomical units distant, approximately 270 million kilometers from Earth. Far enough to pose no threat, yet close enough for detailed spectroscopic analysis by our most advanced instruments. It was as if the universe had delivered a meticulously packaged sample from another star system directly to our astronomical doorstep, complete with optimal viewing conditions and a generous time frame for study. But why now? What explained this sudden surge of celestial activity converging within a few weeks? Enhanced observational capabilities certainly played a role. The Vera C. Rubin Observatory had recently captured its inaugural light images in June 2025, yielding thousands of new asteroid detections in approximately 10 hours of operation. More instruments were scrutinizing the sky with unprecedented sensitivity, revealing the true density of small celestial bodies within our solar system. Nevertheless, the timing felt too opportune, too deliberately arranged to be dismissed as mere observational bias. Was there something distinctive about September 2025? A gravitational alignment or seasonal configuration that had drawn these objects together, or were we witnessing the initial phase of a larger phenomenon, a cosmic drama unfolding on timescales far exceeding human comprehension? The prevailing sentiment among astronomers was not fear, but an urgent sense of curiosity. Planetary defense systems had undergone substantial development since the era when impacts were solely the domain of science fiction. We now possess the technological capacity to track, characterize, and even divert potentially hazardous objects. The recent triumph of NASA's DART mission had demonstrated the efficacy of kinetic impactors in altering an asteroid's trajectory, while the European Space Agency's HERA mission was en route to conduct an in-depth examination of the results. However, knowledge and preparedness were contingent upon the warning time they afforded. This brought forth unsettling questions regarding the celestial visitors we had not yet detected, those still approaching from the Sun's direction, obscured by its glare until their final descent. Had FA-22 been on a collision course rather than a safe fly-by trajectory, would we have possessed sufficient advance notice to implement an effective countermeasure? And what insights did 3I Atlas, with its alien chemical makeup and interstellar origins, offer regarding the unseen population of objects traversing the vastness between stars? The September surge had awakened something within the collective scientific consciousness. It was not panic, but a recognition that our solar system was significantly more dynamic and intimately connected to the broader galaxy than previously surmised. We were observing the initial act of humanity's transformation from a solitary planetary species to active participants in galactic-scale events. But first, we needed to comprehend precisely what we were encountering. If FA-22 had impacted Earth instead of safely passing by, what would the consequences have been? Part 2. A detailed examination of FA-22. What if it had struck? The physics of celestial collisions are unforgiving. When asteroid 2025 FA-22 streaked past Earth on September 18th at a distance of 835,000 kilometers, it carried kinetic energy equivalent to approximately 100 megatons of TNT. To put this into perspective, this is roughly 2,000 times more powerful than the atomic bomb that devastated Hiroshima, all concentrated within a single rocky projectile measuring between 130 and 290 meters across. However, energy is only one component of the equation. What is most critical is how that energy is delivered to our planet's surface. This depends entirely on a complex interplay of physical factors, including the atmospheric entry angle, the object's composition, and sheer cosmic fortune. The distinction between a regional catastrophe and a global extinction event often hinges on factors as simple as whether the approaching object is composed of solid iron or loosely aggregated gravel, whether it enters at a steep angle or grazes the atmosphere, and whether it detonates in midair or impacts the ground. FA-22's approach velocity of approximately 10.8 kilometers per second was typical for near-Earth objects, sufficiently fast to compress and heat the atmosphere ahead of it into a plasma sheath, but not so extreme as to suggest an origin from the outer solar system or beyond. At such a speed, atmospheric entry would have been spectacularly violent. The object would have begun to glow like a second sun while still hundreds of kilometers above the surface. Its leading edge would have reached temperatures of several thousand degrees Celsius as it plowed through increasingly dense atmospheric layers. For a stony asteroid of FA-22's size, the most probable outcome would have been an airburst, a complete atmospheric detonation occurring between 5 and 15 kilometers above the surface. This is akin to the Tunguska event in Siberia in 1908, when an estimated 3 to 15 megaton airburst flattened over 2,000 square kilometers of forest without leaving a crater. The FA-22 scenario would have been considerably more potent. Imagine standing 200 kilometers from ground zero on a clear morning. First, the light would appear, a flash brighter than the sun, visible even in daylight, causing retinal damage and igniting clothing and vegetation across hundreds of square kilometers. The thermal pulse would persist for several seconds, sufficient to inflict third-degree burns on exposed skin at distances exceeding 100 kilometers. Then the sound would arrive. The shockwave from a 100 megaton airburst would shatter windows across an area the size of a small country. The overpressure wave would flatten most residential structures within 50 kilometers of ground zero and cause significant structural damage up to distances approaching 150 kilometers. Even robust concrete constructions would sustain severe damage within the inner destruction zone. However, what if FA-22 had been composed of denser material or arrived at a shallower angle, allowing it to penetrate deeper into the atmosphere before fragmenting? The crater scenario presents a distinct form of devastation. Utilizing established impact modeling programs, such as Impact Earth, we can estimate that a 200-meter iron asteroid striking at 10 kilometers per second would excavate a crater approximately 3 kilometers in diameter and 500 meters deep. The immediate effects would be apocalyptic for anyone within visual range. The impact would vaporize the asteroid and an equivalent mass of target rock, propelling millions of tons of superheated debris on ballistic trajectories that would rain burning material across thousands of square kilometers. The seismic shock would register as a magnitude 6.5 earthquake, collapsing buildings and triggering landslides across a region hundreds of kilometers wide. Yet perhaps the most alarming scenario would be an ocean impact. Over 70% of Earth's surface is covered by water, making this statistically the most likely outcome for any randomly approaching asteroid. When celestial projectiles strike the ocean, they do not simply vanish into the depths with a large splash. They generate something far more perilous: tsunamis. The physics of impact-generated tsunamis are still being refined by researchers, but recent modeling suggests that even a 250-meter asteroid impacting the deep ocean would produce initial wave heights exceeding 100 meters at the impact site. These waves would propagate outward at speeds comparable to jet aircraft, carrying sufficient energy to remain destructive across entire ocean basins. An FA-22-sized impact in the mid-Atlantic could potentially send 10-meter waves crashing into coastal cities from Boston to Barcelona within hours of impact. However, there is a crucial caveat that often gets overlooked in disaster simulations. Wave height diminishes with distance. Classic hydrocode simulations indicate that tsunami waves lose energy as they travel, with typical height reductions following predictable mathematical patterns. A devastating 100-meter wave at the impact site might be reduced to 10 meters by the time it travels 60 kilometers and continue to diminish as it traverses ocean basins. The critical details, as always, lie in the intricacies of coastal geography and local bathymetry. The question of regional versus global impact is paramount for understanding the true threat posed by city-killer-sized asteroids. An FA-22 impact would undoubtedly result in regional devastation, potentially affecting millions of individuals, but it would be unlikely to trigger global climatic effects or endanger human civilization as a whole. That level of destruction necessitates significantly larger impactors, objects in the kilometer-plus size range that strike perhaps once every few 100,000 years. For comparative purposes, consider the Chelyabinsk event of February 15, 2013. That 20-meter asteroid generated an airburst equivalent to approximately 500 kilotons of TNT, injured over 1,500 people, primarily through flying glass from shattered windows, and provided the world with dramatic dashcam footage of what occurs when cosmic debris encounters modern civilization. The Chelyabinsk object was roughly 1/10 the diameter of FA-22, underscoring how rapidly impact energy scales with size. What made Chelyabinsk particularly concerning for planetary defense experts was not the damage it inflicted, but the fact that it arrived completely undetected. The asteroid approached from the direction of the Sun, concealed within the solar glare until the final moments before atmospheric entry. No telescope on Earth observed its approach. This represents one of the fundamental blind spots in our current detection network. The Sunward Approach Corridor, where even city-killer-sized objects can arrive with virtually no warning. FA-22's safe flyby actually provided valuable real-world experience for international planetary defense coordination. The asteroid's brief appearance on the European Space Agency's risk assessment list, followed by its removal after additional observations refined its orbit, offered agencies practice in the delicate art of public communication regarding potentially hazardous objects. How does one inform the public about a possible threat without inciting panic? How are international response efforts coordinated when dealing with objects that could impact multiple nations? The International Asteroid Warning Network conducted what amounted to a live exercise during FA-22's approach, testing communication protocols and observation coordination procedures that would be essential in a genuine emergency. The fact that it ultimately proved to be a false alarm did not diminish the value of the exercise. In fact, it provided something even more beneficial, proof that the system could function under pressure. However, the exercise also highlighted critical deficiencies that persist in our planetary defense capabilities. Lead time is of utmost importance in asteroid deflection. The sooner a potentially hazardous object is detected, the lesser the deflection required to safely alter its trajectory. A gentle nudge applied years in advance can obviate the need for desperate last-minute measures. Current deflection technologies, validated by NASA's successful DART mission, rely primarily on kinetic impact, essentially playing cosmic billiards with asteroids using high-speed spacecraft. This technique is effective but demands precise knowledge of the target's composition, structure, and rotational state. A rubble pile asteroid responds very differently to impact than a solid iron mountain, and miscalculations in these parameters could mean the difference between successful deflection and catastrophic fragmentation. The FA-22 scenario serves as a stark reminder that we inhabit a planet situated within a shooting gallery of cosmic debris. Most of this material consists of harmless sand grain-sized particles that burn up without incident in our atmosphere as meteor showers, but occasionally something larger slips through the gaps in our detection network. And when it does, the repercussions can be devastating on scales ranging from city blocks to entire civilizations. The encouraging news is that we are becoming more adept at this cosmic neighborhood watch. New survey telescopes are coming online with unprecedented capabilities to detect and track potentially hazardous objects, while space-based infrared observatories will soon close the sunward detection gap that allowed Chelyabinsk to arrive unannounced. Yet as we have grown more proficient at cataloging the threats in our immediate solar system vicinity, we have also begun to realize the extent of our ignorance regarding the broader cosmic environment. Objects like 3I Atlas remind us that our solar system is not an isolated entity, but rather a waypoint along the galactic highway, constantly receiving visitors from the vast expanses between stars. This raises an intriguing question regarding the September convergence. Were we witnessing a random gathering of unrelated objects? Or could there be deeper connections between FA-22, the other near-Earth asteroids, and the enigmatic interstellar visitor that dominated astronomical headlines. Before we can address that question, we must understand what else shared the cosmic stage during those remarkable autumn weeks. Part 3. Swan, Apophis, and the Comet Surge. While asteroid FA22 garnered significant attention due to its close passage, another celestial entity was subtly preparing for its appearance in the evening sky. Comet C2025-R2, discovered by the Solar Wind Anisotropies instrument aboard the SOHO spacecraft on September 11th, was rapidly intensifying in brightness, approaching naked-eye visibility as it descended toward the Sun. Unlike the predictable and well-mapped trajectory of FA22, this comet represented something far more volatile and unpredictable. Swan's discovery of the comet highlighted one of the most elegant aspects of contemporary space-based astronomy. The instrument was not designed for comet hunting. Its primary mission involves mapping hydrogen emissions resulting from solar wind interactions at the edge of our solar system. However, it transpires that as comets begin their final approach toward the Sun, they release hydrogen-rich water vapor in quantities detectable from millions of kilometers away. Swan, in essence, stumbles upon new comets by observing their hydrogen signatures erupting against the backdrop of interplanetary space. By mid-September, SIAP 2025-R2 had brightened to approximately 6 magnitude, hovering right at the threshold of naked-eye visibility under dark, rural skies. Amateur astronomers began reporting sightings near the constellation Virgo, in proximity to the bright star Spica, and the reddish hue of Mars in the western sky after sunset. The celestial body's trailing vapor stream was extending and becoming more defined as solar warmth induced volatile frozen substances to vaporize from its core, forming the familiar hazy envelope and tail that has captivated human minds for countless centuries. However, comets are known for their extreme fragility. Unlike the sturdy rock and metal makeup of asteroids, comets are essentially frozen mixtures of ice, dust, and organic compounds, loosely bound together by weak gravitational forces and frozen volatiles. As they draw nearer to the Sun, the very heat that sculpts their magnificent tails can also cause them to shatter completely. Many comets observed by Swan do not survive their initial close encounters with solar energy, breaking apart into streams of debris that create fleeting meteor showers before vanishing entirely. The science behind cometary activation involves a sophisticated interplay of vaporization temperatures and solar heating. Water ice begins to sublimate at temperatures around 200 Kelvin, while more volatile compounds, such as carbon dioxide and methane, start to release gases at even greater distances from the Sun's position. As these materials transform directly from solid to gas, they generate streams of vapor that can significantly alter a comet's path through non-gravitational forces. This renders comet orbits notoriously challenging to predict with high accuracy, especially for objects making their inaugural passage from the distant Oort cloud. Object SIAP 2025-R2's chances of survival remained uncertain throughout September. Newly arrived comets from the outer solar system frequently contain pristine ices that have never been exposed to substantial solar warmth. Upon finally encountering the Sun's radiation, the rapid sublimation process can induce internal pressures that exceed the comet's structural strength. The nucleus might fracture into multiple pieces, each developing its own tail and coma, or it could disintegrate entirely into an expanding cloud of fragments. Yet even as this new comet attracted the attention of amateur astronomers, another celestial notable was preparing for its own moment in the limelight. Asteroid 99-942. Apophis, the 400-meter-wide mass of rock that once topped every planetary defense concern list, continues its inevitable approach toward the closest asteroid passage in recorded human history. On April 13, 2029, Apophis will sweep past Earth at a distance of merely 32,000 kilometers, closer than our geostationary communication satellites. This proximity will allow it to appear as a bright, rapidly moving star, visible to the naked eye, even from urban areas. The flyby will occur at approximately 50,000 kilometers per hour, meaning observers will be able to witness the asteroid's movement against the starscape in real time without the aid of telescopes. What makes the Apophis encounter scientifically enthralling is that we know with absolute certainty it poses no impact risk for at least the next century. Radar observations and optical tracking have refined its orbit to an extraordinary degree of precision, eliminating any possibility of collision during the 2029 flyby or for decades thereafter. This allows scientists to concentrate entirely on the remarkable opportunity to study a large asteroid during an exceptionally close passage. The gravitational influences exerted by Earth during the flyby will be profound and permanent. Apophis will experience tidal forces strong enough to alter its rotational speed, modify its surface features, and potentially trigger landslides or the redistribution of regolith across its entire surface. The asteroid that emerges from this encounter will be measurably different from the one that approached, providing a natural laboratory for understanding how close planetary encounters reshape smaller bodies over geological timescales. NASA's OSIRIS-APEX mission, a repurposed variant of the successful OSIRIS-REx sample return spacecraft, is already en route to rendezvous with Apophis shortly after the 2029 flyby. The spacecraft will spend months mapping the asteroid's post-encounter surface, measuring how the gravitational interaction with Earth has affected its physical properties and internal structure. This data will prove invaluable for future asteroid deflection missions, which must account for how target objects respond to external forces. The timing of Apophis's approach, occurring just 3.5 years after the September 2025 search, raises intriguing questions about whether we are entering a period of increased near-Earth object activity. Statistically speaking, close asteroid passages do not adhere to any particular schedule. They are essentially random occurrences governed by the complex gravitational interactions that shape the solar system over billions of years. Yet the clustering of significant encounters within such a brief time frame seems to challenge the notion of purely random distribution. Part of this apparent increase stems from observational bias. The completion of major asteroid surveys like Linear and Spacewatch over the past 2 decades has dramatically improved our capacity to detect and track potentially hazardous objects. The Vera C. Rubin Observatory, which captured its first light images in June 2025, represents another quantum leap in survey capability. Its vast field of view and sensitive detectors will rescan the entire accessible sky every few nights, providing an unprecedented frequency for discovering new objects and monitoring known ones. However, improved detection capabilities alone do not explain the September surge or the remarkable variety of objects involved. Alongside FA-22's close approach and C-2025-R2's brightening display, dozens of smaller near-Earth objects threaded their way through our local cosmic neighborhood. Object 2025 RJ2 passed at a distance of just 0.78 lunar distances on September 15th. Multiple sublunar distance encounters occurred throughout the month, each catalogued and tracked by the Global Space Surveillance Network. The seasonal timing might offer clues about the underlying dynamics. Earth's orbital motion carries us through different regions of the inner solar system throughout the year, and it is possible that September 2025 corresponded to our passage through a particularly populated zone of space debris. Alternatively, the apparent clustering might result from complex gravitational resonances that can synchronize the orbits of multiple objects over geological timescales. Comets add another layer of complexity to this cosmic choreography. Unlike asteroids, which follow relatively stable and predictable orbits, comets can experience dramatic changes in trajectory due to outgassing forces and gravitational perturbations from the giant planets. Long-period comets from the Oort cloud arrive with essentially no advanced warning, following orbits that have not brought them into the inner solar system for thousands or millions of years. The distinction between asteroids, comets, and meteors often confuses public discussions of planetary defense. Yet these differences are crucial for understanding impact risks and mitigation strategies. Asteroids are essentially rocky or metallic masses in space, following well-defined orbits that change slowly over time. Comets are volatile-rich objects whose behavior can be unpredictable due to outgassing effects. Meteors are simply the visible light phenomena created when small particles burn up in Earth's atmosphere, regardless of whether their parent body was an asteroid or a comet. This diversity of small body types reflects the complex history of our solar system's formation and evolution. The asteroid belt between Mars and Jupiter contains remnants of planetary formation that never successfully assembled into a planet. while comets preserve samples of the primitive ices and organics from the outer reaches of the early solar nebula. Each population tells part of the story of how worlds form around stars, and each presents different challenges for planetary defense. As autumn 2025 progressed, the cosmic stage was set for even more remarkable revelations. The September surge of familiar solar system objects was about to be overshadowed by something unprecedented. A visitor from another star system entirely, carrying chemical signatures that would challenge fundamental assumptions about planetary formation and the nature of interstellar space. But first, this mysterious traveler would have to navigate the complex gravitational environment of our inner solar system while remaining hidden behind the solar glare during its closest approach to the Sun's position. When it finally emerged into telescopic view in early December, 3I Atlas would prove to be unlike anything astronomers had ever seen before. Part 4. The Interstellar Intruder. On July 1, 2025, a routine automated sky survey captured something extraordinary disguised as an unremarkable dot of light. The Atlas Telescope Array at Rio Hurtado, Chile, had photographed thousands of such objects, asteroids, comets, and distant stars shifting position against the stellar background. But this particular dot would soon rewrite our understanding of what travels between the stars. Initially catalogued as just another potential near-Earth object, the object that would become known as 3I Atlas appeared no different from countless other discoveries in the Atlas database. The automated systems flagged it for follow-up observations based on its apparent motion across the sky. And within days, telescopes around the world were tracking its trajectory with increasing precision. It was during this routine astrometric follow-up that astronomers realized they were dealing with something unprecedented. The mathematics were unmistakable. As more observational data refined the object's orbital elements, one parameter stood out with startling clarity. Its orbital eccentricity exceeded unity. In celestial mechanics, this is the signature of a hyperbolic trajectory, an orbit carrying more than enough velocity to escape the Sun's gravitational influence entirely. This object wasn't bound to our solar system. It was just passing through. 3I Atlas became only the third confirmed interstellar visitor in human history, following the mysterious cigar-shaped object, 1I Oumuamua in 2017 and Comet 2I Borisov in 2019. But unlike those previous visitors, 3I Atlas arrived with perfect timing for extensive observation. Its trajectory would carry it to perihelion, closest approach to the Sun, on approximately October 30th, 2025, followed by its closest approach to Earth in December at a distance of roughly 1.8 astronomical units. That December distance translates to approximately 270 million kilometers, far enough to pose absolutely zero threat to Earth, but close enough for detailed spectroscopic analysis by our most powerful telescopes. It was as if the cosmos had arranged a cosmic delivery service, dropping off a pristine sample from another star system with optimal viewing conditions and plenty of advance notice. But the object's trajectory was only the beginning of its mysteries. As observational data accumulated throughout the summer and early autumn of 2025, 3I Atlas began displaying characteristics that challenged assumptions about both interstellar space and comet behavior. Size estimates from Hubble Space Telescope observations suggested an upper limit of approximately 5.6 kilometers for the nucleus, though the actual size was likely significantly smaller. This placed it in the intermediate range between typical comet nuclei and small asteroids. What truly set 3I Atlas apart from its interstellar predecessors was its unmistakably cometary behavior. Unlike 1I Oumuamua, which showed no visible coma or tail despite its puzzling non-gravitational acceleration, 3I Atlas developed a classic cometary appearance as it approached the Sun's position. By September, ground-based telescopes were resolving a substantial coma, the cloud of dust and gas surrounding the nucleus, along with the beginnings of what would become an impressive tail structure. This cometary activity provided the first clues to the object's truly alien chemistry. When the James Webb Space Telescope turned its infrared spectrographs toward 3I Atlas in late summer 2025, the results were unlike anything seen in solar system comets. The object's coma showed an unusually high ratio of carbon dioxide to water vapor, among the highest CO2 to H2O ratios ever measured in a comet. To understand why this chemistry is so significant, consider how comets form in typical planetary systems. Water ice condenses from the protoplanetary nebula at temperatures around 150 Kelvin, corresponding to orbital distances of approximately 2 to 3 astronomical units from a Sun-like star. Carbon dioxide, with its lower sublimation temperature, condenses much farther out, beyond the snowline where temperatures drop below 78 Kelvin. The extreme CO2 dominance in 3I Atlas suggests formation in the frigid outer regions of its parent planetary system, far beyond where most solar system comets originate. Either this object condensed from a protoplanetary disk that was unusually rich in carbon dioxide, or it formed so far from its parent star that water ice never had a chance to accumulate in significant quantities. But the chemical anomalies didn't stop with carbon dioxide. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent nickel emission lines with surprisingly weak iron signatures. In typical solar system comets, iron and nickel occur in roughly solar proportions, reflecting the composition of the stellar nebula from which they condensed. The apparent depletion of iron relative to nickel in 3I Atlas hints at chemical processing or formation conditions unlike anything in our local cosmic neighborhood. As autumn progressed and 3I Atlas continued its approach toward perihelion, its tail structure became increasingly complex and visually spectacular. The Gemini Observatory and other ground-based facilities documented multiple tail components with different orientations and compositions, suggesting ongoing activation of volatile materials across different regions of the nucleus. The object was literally coming alive under solar heating after potentially billions of years in the cold emptiness between stars. The timeline for observing 3I Atlas presented both opportunities and challenges. As it approached perihelion in late October, the comet would become increasingly difficult to observe from Earth due to its proximity to the Sun in our sky. Solar glare would effectively hide the object during its most active phase, when thermal processing might reveal additional clues about its composition and internal structure. But patience would be rewarded. Earth's orbital motion would gradually improve the viewing geometry throughout November, and by early December, 3I Atlas would emerge from behind the solar glare into prime observing position. At closest approach to Earth in mid-December, the object would still be nearly 200 times farther away than the Moon, but well-positioned for extended spectroscopic campaigns by major observatories. The intervening months of hidden observation presented a tantalizing mystery. What changes would occur as 3I Atlas reached peak solar heating? Would its unusual chemistry remain stable, or would the intense radiation drive off surface materials to reveal different compositions beneath? Most importantly, would the object survive perihelion intact, or would thermal stresses fragment it into multiple pieces like so many comets before it? Preliminary kinematic modeling suggested that 3I Atlas might be extraordinarily old, possibly more than 7 billion years. If recent calculations linking it to the galaxy's thick disk population proved correct, this would make it older than our entire solar system, a wanderer that had been drifting through interstellar space since before Earth existed. The chemical signatures preserved in its ices and rocky components could provide direct samples of conditions in the early galaxy when star formation rates and heavy element abundances were dramatically different from today. Unlike 1I Oumuamua's brief visit and rapid departure, 3I Atlas offered the prospect of extended study across multiple observing seasons. Its moderate approach velocity and favorable geometry would keep it within range of major telescopes well into 2026, providing an unprecedented opportunity to characterize an authentic piece of another star system. But even as astronomers prepared for months of detailed observations, nagging questions remained about the object's origins and journey to our solar system. How long had it been wandering in interstellar space? What star system had ejected it? And under what circumstances? Most intriguingly, was its arrival during the same period as the September asteroid surge purely coincidental? Or could there be deeper connections between the interstellar visitor and the unusual clustering of near-Earth object encounters? The apparent synchronization of cosmic events was beginning to strain credibility. First, the parade of close-approaching asteroids, then the brightening comet, And finally, the emergence of an interstellar visitor with unprecedented chemical signatures. Either we were witnessing an extraordinarily unlikely convergence of unrelated phenomena, or something more fundamental was orchestrating this celestial performance. As 3I Atlas continued its descent toward perihelion, hidden behind the growing solar glare, astronomers could only speculate about what revelations awaited its December reemergence. But already the object had begun to reveal secrets that would reshape our understanding of planetary formation, interstellar chemistry, and our place in the galactic community. The question was no longer whether this visitor would provide new insights into the cosmos. It was whether we were prepared for the implications of what it might reveal about the universe beyond our solar system's boundaries. The real mystery, however, was only beginning to unfold. Because while 3I Atlas dominated scientific attention with its alien chemistry and ancient origins, a growing number of researchers were starting to notice patterns in the September surge that suggested something more than random cosmic coincidence was at work. Part 5. Planetary Defense Wake-Up Call. The September 2025 surge served as an uncomfortable reminder of just how precarious our planetary defense capabilities remain, despite decades of technological advancement and international cooperation. While we successfully tracked and characterized every significant object that approached Earth during those eventful weeks, the clustering of encounters highlighted critical gaps that could prove catastrophic if filled by the wrong kind of visitor at the wrong time. Consider the fundamental challenge of detection geometry. The vast majority of our asteroid-hunting telescopes are ground-based facilities that can only observe objects when they're sufficiently separated from the Sun in our sky. This creates a massive blind spot in the direction of our nearest star. Precisely the approach corridor that delivered the Chelyabinsk impactor completely undetected in 2013. An asteroid approaching from the sunward direction remains effectively invisible until the final hours or minutes before atmospheric entry. FA-22's trajectory fortunately carried it well clear of this detection shadow, allowing telescopes worldwide to track its approach for weeks before closest passage. But if its orbit had been inclined differently, or if its approach vector had aligned more closely with the Sun-Earth line, we might have had mere days or hours of warning instead of the comfortable lead time that allowed detailed characterization and public notification. This sunward blind spot represents one of the most significant vulnerabilities in our current planetary defense architecture. Ground-based observation efforts have achieved significant advancements in cataloging objects that pose a threat to Earth, yet their capabilities are inherently constrained by the fundamental principles of optics and celestial mechanics. It is impossible to detect objects concealed by the Sun's brilliance, regardless of the sophistication of the telescope employed. The logical solution necessitates relocating detection systems into space, enabling them to operate independently of Earth's diurnal cycle and atmospheric disturbances. NASA's impending Near-Earth Object Surveyor mission, slated for a September 2027 launch, will deploy an infrared space telescope specifically engineered to track asteroids from a vantage point trailing Earth in its orbit around the Sun. From this unique position, NEO-Surveyor will be capable of identifying celestial bodies approaching from directions imperceptible to ground-based observatories. However, the detection of objects from space represents merely the initial phase in a multifaceted system of planetary defense mechanisms. Once a potentially hazardous object is identified, it must be thoroughly characterized to ascertain the true level of danger and to devise the most effective mitigation strategy. This process demands prompt follow-up observations from multiple observatories, precise orbit determination, and in-depth analysis of the object's physical attributes. The Vera C. Rubin Observatory, which captured its inaugural light images in June 2025, signifies a groundbreaking leap forward in these follow-up capabilities. Its colossal mirror and expansive field camera possess the ability to resurvey the entire observable sky every 3 nights, offering an unparalleled frequency for monitoring newly discovered objects and their orbital trajectories. Within its initial 10 hours of operation, Rubin registered thousands of new asteroid detections, underscoring the instrument's potential to substantially augment our census of near-Earth objects. Nevertheless, detection and tracking are rendered futile without the capacity to actively address impending threats. This is where NASA's Double Asteroid Redirection Test Mission has provided invaluable real-world validation of kinetic deflection technology. The DART spacecraft's impact with asteroid Dimorphos on September 26, 2022 successfully altered the smaller asteroid's orbital period by 32 minutes, far surpassing the minimum 4-minute adjustment required to confirm mission success. More significantly, comprehensive analysis of the impact revealed that the momentum transfer efficiency, known as beta, was approximately 3.6, indicating that the impact was nearly 4 times more effective than would be predicted by simple momentum conservation. This amplification factor arises from the ejection of debris following the impact, which acts akin to rocket exhaust, enhancing the deflection effect. Comprehending this physical phenomenon is paramount for the design of future deflection missions. The European Space Agency's HERA mission, currently en route to the Didymos system, is scheduled to arrive in 2026 to conduct an exhaustive forensic examination of the DART impact site. HERA's detailed mapping and measurement of the crater and debris field will furnish empirical data for impact models, thereby refining our understanding of how different asteroid types respond to kinetic deflection attempts. However, kinetic impact represents but one component of the comprehensive planetary defense arsenal. For larger objects or situations necessitating more precise trajectory adjustments, alternative methodologies may prove more advantageous. Gravity tractors, spacecraft that employ their own gravitational influence to subtly alter an asteroid's course, can accumulate velocity changes over extended periods, spanning years or decades. Nuclear standoff devices possess the capability to vaporize surface material, generating potent rocket-like thrust. Ion beam shephers could utilize focused particle beams to gradually ablate one side of an asteroid, producing continuous low-level propulsion over prolonged durations. The pivotal realization stemming from planetary defense research is that all these approaches demand considerable lead time to be effective. A gentle redirection applied years or decades in advance can obviate the necessity for desperate, last-minute interventions. This underscores the critical importance of early detection. It is not merely to provide time for urban evacuation or the construction of subterranean shelters, but because subtle deflections become exponentially more manageable with advance notice. The International Asteroid Warning Network, established to coordinate a global response to potential impact threats, conducted what effectively amounted to a live exercise during the approach of Asteroid 2025 FA22. The asteroid's brief inclusion on the European Space Agency's risk assessment list, followed by its subsequent removal after additional observations, provided valuable experience in navigating the delicate equilibrium between public information dissemination and the prevention of undue panic. How can the world be apprised of a potential asteroid threat without precipitating economic turmoil or societal disruption? How can international cooperative efforts be coordinated when dealing with objects that could affect numerous nations? These questions lack straightforward answers, but the flyby of FA22 presented a relatively low-risk opportunity to test communication protocols and decision-making processes. The exercise illuminated both the strengths and weaknesses of our present approach. The swift international exchange of observational data facilitated a rapid refinement of FA22's orbit and its prompt removal from risk assessment lists once the threat was mitigated. However, public communication remained inconsistent, with certain media outlets sensationalizing the initial risk assessment, while others entirely disregarded the event until after its safe passage was confirmed. A contributing factor to this communication challenge stems from the inherent uncertainty present in early orbital determinations. When an asteroid is first discovered, its projected trajectory is poorly defined due to limited observational data. The region of uncertainty, encompassing the range of possible orbits consistent with available measurements, can include both impact and near-miss scenarios. Only supplementary observations can sufficiently narrow this uncertainty to enable definitive predictions. This creates a fundamental dilemma in planetary defense communication. Delaying notification until the probability of impact drops to zero risks forfeiting valuable preparation time if the object is indeed on a collision course. Conversely, releasing information while significant uncertainty persists risks provoking unwarranted alarm or, worse, public skepticism if the threat assessment is revised as superior data becomes available. The September surge also underscored remaining deficiencies in our detection capabilities, notwithstanding recent advancements. Long-period comets originating from the outer solar system can still materialize with relatively short notice, as their highly elliptical orbits are primarily situated in distant regions where they remain undetectable. Comet Swift-Tuttle, for instance, is not expected to return to the inner solar system until 2026, yet its nucleus is estimated to be 26 kilometers in diameter, sufficiently large to inflict global devastation should its orbit intersect Earth's path. Perhaps most disconcerting are the city-killer-sized objects, ranging from 100 to 300 meters in diameter. These are large enough to cause regional destruction, but small enough to remain difficult to detect until they are in close proximity to Earth. Current surveys have catalogued the majority of the kilometer-plus objects capable of worldwide devastation, but the inventory of smaller, potentially hazardous asteroids remains incomplete. The September events also prompted uncomfortable inquiries regarding our capacity to manage multiple simultaneous threats. While FA-22 dominated headlines, dozens of smaller objects were concurrently traversing our immediate cosmic vicinity. If several city-killer-sized asteroids were approaching concurrently from disparate directions, would our tracking and characterization resources be overwhelmed? Would we possess the technological and logistical capacity to implement deflection missions against multiple targets simultaneously? These scenarios remain hypothetical, but they emphasize the imperative of sustained investment in planetary defense infrastructure. The completion of the Vera C. Rubin Observatory Survey, the deployment of NEO Surveyor, and the ongoing development of deflection technologies represent crucial strides toward a truly robust planetary defense capability. However, they also signify merely the commencement of what will undoubtedly be a multi-generational endeavor to safeguard human civilization from cosmic impacts. The encouraging news is that planetary defense is fundamentally a surmountable challenge. Unlike seismic events, volcanic eruptions, or other natural catastrophes, asteroid impacts are entirely preventable with adequate advance warning and appropriate technology. The physics governing deflection are well understood. The requisite technologies are within our current grasp, and a framework for international cooperation already exists. What is now required is the political resolve to maintain funding and support for these systems during the extended intervals between significant impact threats. Planetary defense functions much like insurance. It appears superfluous until the precise moment it becomes desperately necessary. The September surge served as a valuable reminder that we inhabit a dynamic cosmic environment, where impacts are not a question of if, but when. Yet as astronomers diligently worked to catalogue and characterize the parade of near-Earth objects during those eventful autumn weeks, a different kind of enigma began to surface from the observational data. The timing of these encounters, the clustering of their trajectories, and the remarkable coincidence of an interstellar visitor arriving within the same narrow temporal window began to strain the limits of statistical probability. Were we witnessing an exceptionally improbable confluence of unrelated events, or was a more profound influence orchestrating this cosmic ballet? Part 3. Atlas. The human brain is exquisitely wired to perceive patterns, even in their absence. This evolutionary adaptation aided our ancestors in spotting hidden predators amidst tall grass and recognizing seasonal shifts vital for survival. However, when applied to astronomical phenomena, this same pattern recognition system can lead us astray, discerning connections and conspiracies within the random fluctuations of cosmic occurrences. Yet occasionally the patterns are indeed real. Consider the chronological sequence. Asteroid 2025, FA-22 sweeps past Earth on September 18th at a distance of 2.2 lunar distances. 3 days prior, a smaller object, 2025 RJ2, passes at a mere 0.78 lunar distances. Throughout that same week, numerous additional near-Earth objects are tracked by global surveillance networks. Comet C2025 R2 brightens, becoming visible to the naked eye in the evening sky. And lurking in the background, the interstellar visitor 3I Atlas approaches its October perihelion after a journey that may have spanned billions of years. Individually, none of these events is particularly extraordinary. Dozens of asteroids traverse within 0.05 astronomical units of Earth each month, adhering to orbital mechanics established billions of years ago. Comets regularly exhibit fluctuations in brightness as they approach and recede from the Sun's orbit. Interstellar objects, while rare, are anticipated outcomes of planetary formation and evolution around other stars. However, the convergence of these events within such a compressed temporal frame begins to challenge simplistic explanations based on cosmic happenstance. What are the odds that an interstellar visitor would arrive during the same month as a period of unusually heightened near-Earth object activity? How probable is it that a newly discovered comet would reach peak visibility precisely as multiple asteroids are making close approaches? One speculative avenue worthy of exploration involves gravitational shepherding. The possibility that the passage of 3I Atlas through the inner solar system could, in some manner, influence the trajectories of smaller objects. Large celestial bodies can exert gravitational perturbations on smaller ones, potentially creating a stream of debris or an entourage effect that might account for the clustering of September encounters. Nevertheless, the prevailing physics strongly militates against this scenario. 3I Atlas, even at its estimated maximum size of approximately 6 kilometers, lacks sufficient mass to gravitationally influence objects at distances of millions of kilometers. Newton's inverse square law dictates that gravitational effects diminish rapidly with distance, becoming negligible at the scales relevant to the September encounters. Furthermore, the orbital characteristics of the various September visitors exhibit no evidence of a common origin or shared dynamical history. FA22 follows a typical near-Earth object orbit with modest eccentricity and inclination. The smaller asteroids detected throughout the month display the full spectrum of orbital attributes anticipated from the background population of near-Earth objects, with none exhibiting the hyperbolic trajectories that would suggest recent gravitational interaction with an interstellar intruder. A more plausible explanation for the apparent clustering lies in observational bias and detection cadence effects. The Vera C. Rubin Observatory had recently achieved first light in June 2025, dramatically enhancing our capacity to detect and track small near-Earth objects. Increased survey coverage naturally leads to an uptick in discoveries, creating the impression of heightened activity, even if the underlying population remains constant. Consider it akin to suddenly installing high-definition surveillance cameras in a previously unmonitored area. The number of individuals passing through the space has not changed, but your awareness of their presence is dramatically amplified. Similarly, improved astronomical surveys reveal the true density of near-Earth objects that were always present, but simply eluded detection by less sensitive instruments. The psychological phenomenon of epiphania, the tendency to perceive meaningful patterns in random data, may also be influencing our interpretation of the September events. Once the initial few close approaches were reported, both astronomers and the public became acutely aware of subsequent discoveries. Objects that might have passed unnoticed during a less eventful news cycle suddenly garnered front-page attention, fostering a feedback loop that amplified the perception of unusual activity. However, even when accounting for observational bias and psychological influences, certain aspects of the September surge remain challenging to explain through purely random processes. The discovery of 3I Atlas on July 1st, with its trajectory precisely timed to achieve maximum visibility concurrently with peak near-Earth object activity, represents a remarkable coincidence that pushes the boundaries of statistical probability. Consider an alternative speculative scenario. Could 3I Atlas be not a solitary object, but rather the most substantial member of a fragmented cluster of interstellar material? If the original parent body had fractured during its extensive journey through space, perhaps due to internal stresses or collisions with interstellar dust, the resultant debris stream might be dispersed across a considerable volume of space. In this hypothetical context, the September asteroid encounters could represent smaller fragments originating from the same parent object, following slightly divergent trajectories that bring them into Earth's vicinity at staggered intervals. These fragments would retain their interstellar velocity characteristics but might have been gravitationally captured into temporary solar orbits during previous traversals of the inner solar system. Nevertheless, this fragmentation hypothesis encounters considerable observational hurdles. Spectroscopic analysis of the September asteroids reveals typical carbonaceous or silicate compositions consistent with solar system origins. Their reflective spectra, where available, align with known asteroid taxonomic classifications rather than the unusual chemical profile exhibited by 3I Atlas. If these objects shared a common interstellar genesis, one would anticipate observing analogous chemical signatures across the entire population. Furthermore, the orbital dynamics do not support a shared origin scenario. True interstellar fragments would exhibit hyperbolic orbits, similar to 3I Atlas itself, rather than the elliptical trajectories characteristic of gravitationally bound solar system objects. The energetic requirements for capturing interstellar debris into stable near-Earth object orbits exceed the energy available through gravitational interactions with the planets. Perhaps the most straightforward explanation is also the most probable. We are observing the statistical equivalent of multiple lightning strikes, improbable individual events that occasionally converge through sheer chance. The universe does not obligate itself to distribute cosmic encounters evenly across human timescales. Random processes can and do generate apparent patterns that seem significant to pattern-seeking intelligence. The rapid expansion of survey capabilities in the mid-2025s means we are observing this cosmic neighborhood with unprecedented sensitivity and frequency. Prior generations of astronomers might have entirely missed the majority of the September encounters, or detected them as isolated events spread across different news cycles. Our current ability to discover, track, and characterize multiple near-Earth objects simultaneously creates opportunities for perceived clustering that did not exist during earlier eras of astronomical observation. Yet even as rational analysis points toward coincidence and observational bias, an insistent sense of orchestrated timing persists. The precise arrival of 3I Atlas during a period of heightened near-Earth object activity, coupled with its unprecedented chemical signatures and ancient origins, suggests that we may be witnessing something more profound than a random convergence of unrelated occurrences. The definitive answer may not emerge until we have had months to meticulously study 3I Atlas in detail following its December re-emergence from solar glare. Comprehensive spectroscopic analysis, precise trajectory measurements, and careful comparison with the September asteroid population could potentially reveal connections that are not apparent in preliminary observations. However, if no such connections are found, if 3I Atlas proves to be genuinely independent of the September encounters, then we are confronted with an even more intriguing possibility. Perhaps the universe is simply more active and interconnected than our Earth-centric perspective typically permits us to apprehend. What appears to be an extraordinary convergence from our limited viewpoint might actually be commonplace on galactic scales. The pertinent question is not whether something is following 3I Atlas, but rather whether we are finally developing the observational capacity to perceive the true complexity of the cosmic environment we have always inhabited. And if that is indeed the case, then the September surge may represent merely the initial phase of our education regarding what it signifies to be citizens of a galaxy where 400 billion stars perpetually exchange material across the vast expanse of interstellar space. However, before we can address those broader questions, we must first comprehend the reasons behind 3I Atlas's peculiar behavior. Because as autumn progressed and the interstellar visitor drew nearer to its closest solar proximity, telescopes worldwide were documenting activity and chemical signatures unlike anything previously observed in comets, whether of solar system origin or otherwise. Part 7. Peculiar behaviors and unusual characteristics. As 3I Atlas continued its trajectory toward its October perihelion, observatories across the globe began documenting behaviors that challenged fundamental tenets of cometry physics and interstellar chemistry. What had initially appeared to be a relatively straightforward instance of a stray comet from another star system was revealing layers of complexity that seemed to defy established patterns of how such objects ought to behave. The most striking anomaly emerged from observations conducted by the James Webb Space Telescope throughout August and September of 2025. The James Webb Space Telescope's infrared instruments detected a coma composition overwhelmingly dominated by carbon dioxide to a degree never before witnessed. The ratios of carbon dioxide to water observed were among the highest ever recorded for any comet. This composition was not merely peculiar, it bordered on the impossible according to established theories of comet formation and development. To grasp the significance of this peculiar chemistry, let's consider how comets typically originate within planetary systems. Water ice typically coalesces from protoplanetary disks at temperatures around 150 Kelvin, measured from Sun-like stars. This is why most comets in our solar system, which formed in the outer reaches beyond Neptune's orbit, still retain substantial amounts of water ice mixed with other volatile substances. Carbon dioxide, possessing a much lower condensation temperature, only becomes a significant component of comets at distances greater than 10 astronomical units from their parent star, where temperatures plummet below 80 Kelvin. Even then, carbon dioxide generally remains a minor constituent compared to water ice. The extreme prevalence of carbon dioxide in 3I Atlas suggests either its formation under conditions vastly dissimilar to those in our solar system or subsequent modification that selectively diminished water while preserving carbon dioxide. One potential explanation involves a planetary system far larger or colder than our own. If 3I Atlas coalesced from a protoplanetary disk surrounding a low-mass star or from the remote fringes of a system containing multiple gas giants, it could have formed in a region where carbon dioxide ice was the primary volatile substance. In such environments, water might never have condensed in substantial quantities, leading to the extreme compositional ratios observed by the James Webb Space Telescope. Alternatively, the object might have undergone extensive processing during its protracted journey through interstellar space. Bombardment by cosmic rays over millions or billions of years could potentially alter surface chemistry through radiolysis, the process of breaking chemical bonds using high-energy radiation. If this process preferentially eliminated water molecules while leaving carbon dioxide intact, it could account for the current composition without necessitating unusual formation circumstances. However, the chemical anomalies did not end with the carbon dioxide dominance. Spectroscopic observations from the Very Large Telescope in Chile revealed another perplexing characteristic: pronounced emission lines from nickel atoms with surprisingly weak corresponding signatures from iron. This represents a considerable deviation from typical solar system compositions, where iron and nickel are present in roughly solar proportions, reflecting the elemental abundances of the stellar nebula. 3I Atlas raises fundamental questions regarding its origin, environment, or subsequent evolution. One speculative possibility involves the differential processing of metallic components during the object's interstellar transit. Iron and nickel exhibit distinct sublimation temperatures and chemical reactivities. Consequently, prolonged exposure to cosmic radiation or impacts from interstellar dust might selectively remove iron while preserving nickel in more stable chemical forms. Another intriguing hypothesis posits that 3I Atlas formed within a stellar environment characterized by non-solar elemental abundances. If its parent star belonged to a different galactic population, such as the thick disk or halo components, which harbor stars with atypical chemical compositions, the resulting planetary debris might naturally exhibit iron-to-nickel ratios dissimilar to those observed in our local cosmic vicinity. As summer transitioned into autumn and 3I Atlas approached its perihelion in October, its tail structure became increasingly intricate and visually spectacular. Ground-based observations from facilities like the Gemini Observatory documented multiple tail components exhibiting different orientations, colors, and apparent particle sizes. This multi-component structure suggested the ongoing activation of distinct volatile reservoirs across various regions of the nucleus. The physics governing this complex tail development involves the selective sublimation of different ice species. As the comet encounters increasing solar heating, carbon dioxide begins outgassing at considerably greater distances from the Sun than water ice, potentially generating an initial coma and tail structure dominated by carbon dioxide. As the object draws nearer to perihelion, the activation of water ice might trigger a secondary phase of tail development, characterized by different optical properties and dynamical behavior. Polarimetry measurements, which analyze the polarization state of sunlight scattered by the comet's coma and tail, provided further insights into the nature of the dust particles being ejected from the nucleus. The polarization signature indicated dust grains with unusual size distributions or optical properties when compared to typical solar system comets. This could signify either distinct formation processes within the original protoplanetary disk or extensive modifications during its lengthy interstellar journey. One particularly captivating aspect of 3I Atlas's behavior involved apparent episodic brightenings that seemed to occur independently of its distance from the Sun. Most comets exhibit predictable brightening patterns as they approach perihelion, with their luminosity increasing smoothly as their solar distance diminishes. However, 3I Atlas displayed periodic flare-ups, suggesting more complex internal processes. These outbursts might result from the sudden exposure of fresh, volatile-rich material, as surface crusts are eroded by solar heating. Many comets develop insulating mantles of dust and processed organic matter that suppress sublimation until thermal stresses or internal gas pressure rupture these protective layers. When this rupture occurs, the underlying pristine ices can sublimate rapidly, leading to dramatic temporary surges in activity. Alternatively, the episodic behavior might reflect internal structural adjustments as 3I Atlas adapted to solar heating after potentially billions of years spent in the frigid emptiness of interstellar space. Temperature gradients penetrating into the nucleus could instigate subsurface sublimation, fracturing internal ice deposits, exposing new surfaces to solar radiation, and triggering cascading activation events. The rotational behavior of 3I Atlas also appeared anomalous when compared to typical solar system comets. Photometric observations designed to measure brightness fluctuations as the nucleus rotated revealed either an unusually long rotation period or a complex tumbling motion that complicated period determination. This might indicate structural alterations during its interstellar journey or simply reflect the initial angular momentum state from whatever event ejected it from its parent system. Yet perhaps the most unsettling characteristic of 3I Atlas's behavior was how it appeared normal in certain aspects, while being entirely unprecedented in others. The fundamental physics of coma formation, tail development, and volatile sublimation adhered to well-understood principles. Nevertheless, its specific chemical signatures, temporal evolution, and structural characteristics seemed to defy every expectation based on decades of cometry research. This combination of familiar and alien attributes suggested that 3I Atlas represented something genuinely novel in astronomical observation. It was not merely another comet from another star system, but rather a window into planetary formation processes and stellar environments fundamentally different from our local cosmic neighborhood. The object simultaneously affirmed and challenged our understanding of how planetary systems evolve and what kinds of debris they can expel into the galaxy. As 3I Atlas entered its final weeks before perihelion passage and its temporary concealment behind the sun's glare, the accumulating observational evidence depicted an object that defied simple classification. It was clearly a comet, based on its activity and spectroscopic properties. However, its chemistry and behavioral patterns matched no known category of solar system objects. The central question was whether these anomalies were indicative of genuinely exotic physics and chemistry, or simply represented the extreme end of natural variation within planetary system debris. And that question would have to await resolution until December, when 3I Atlas would re-emerge from its solar hiding place, offering telescopes their optimal opportunity for detailed characterization. But even as intensive observations proceeded, a different kind of speculation began to emerge from the data. This was because while 3I Atlas's peculiar behaviors could potentially be explained through exotic yet natural processes, they also raised uncomfortable questions about whether we were encountering something more than just an unusually active comet from another star system. Part 8. Alien Technology or Natural Marvel. In an era dominated by social media and viral conspiracy theories, it was perhaps inevitable that 3I Atlas would eventually face the question that has intrigued every unusual astronomical discovery since the dawn of the space age. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemistry, complex behaviors, and remarkably convenient timing for observation had conspiracy theorists working overtime by late September 2025. The speculation began innocently enough within academic circles, where researchers noted similarities between 3I Atlas and the controversial object Oumuamua, which had sparked debates about possible artificial origins in 2017. Both were interstellar visitors. Both displayed unusual properties that challenged conventional understanding. Both arrived on trajectories that provided excellent observing opportunities for human astronomers. However, the similarities largely ended there, and the differences were profound and telling. Unlike Oumuamua's enigmatic cigar-like shape and mysterious non-gravitational acceleration without visible outgassing, 3I Atlas behaved precisely like what it appeared to be: a comet. It developed a classic coma and tail structure as it approached the Sun's vicinity. Its brightness variations followed predictable patterns based on volatile sublimation. Its trajectory showed the expected gravitational deflection from solar interaction, with additional perturbations easily explained by outgassing forces. Most importantly, 3I Atlas exhibited no signs of controlled or directed motion. Its path through the solar system followed the precise hyperbolic trajectory expected for an unbound visitor under the sole influence of solar gravity. There were no course corrections, no unexplained accelerations, no radio transmissions, and no geometric shapes or artificial structures visible, even under the highest resolution observations available to human telescopes. The scientific method demands extraordinary evidence for extraordinary claims, and the evidence for 3I Atlas consistently pointed towards natural phenomena, albeit natural phenomena unlike anything previously observed in our cosmic neighborhood. Every strange behavior, every unusual chemical signature, every anomalous physical property had plausible explanations rooted in well-established physics and chemistry. Consider the extreme carbon dioxide dominance that made 3I Atlas's chemistry so remarkable. While unprecedented in solar system comets, this composition could easily stem from formation in the outer reaches of an unusual planetary system. Stars with different masses, metallicities, or planetary architectures might naturally produce comets with chemical signatures that appear alien to observers, familiar only with the products of our local solar system. The apparent depletion of iron relative to nickel, while puzzling, could reflect formation in a stellar environment with non-solar elemental ratios or subsequent processing during billions of years of interstellar travel. Cosmic ray bombardment, interstellar dust impacts, and thermal cycling in the frigid depths of space might selectively alter surface compositions in ways that create unusual spectroscopic signatures without requiring any artificial intervention. Even the complex multi-component tail structure and episodic brightening events had precedence in solar system comets. Although admittedly at the extreme end of observed behaviors, Comet Hale-Bopp displayed multiple tail components with different compositions, and Comet Holmes underwent a dramatic outburst that increased its brightness by a factor of nearly 1 million in 2007. Natural processes were clearly capable of producing the kinds of spectacular and unusual behaviors observed in 3I Atlas. The real question was not whether 3I Atlas could be artificial, but rather why people kept asking. Part of the answer lies in the profound psychological impact of contemplating truly interstellar scales. When we observe objects from other star systems, we confront the possibilities that intelligence might exist elsewhere in the galaxy. The human mind evolved to navigate social hierarchies and detect agency in complex environments, naturally seeks signs of purpose or intention in unexplained phenomena. This tendency becomes even stronger when dealing with objects that seem to defy our expectations or display properties that push the limits of conventional explanation. 3I Atlas's unusual chemistry and convenient observing geometry triggered the same pattern recognition systems that our ancestors used to identify potential predators or allies. When faced with something unprecedented, the brain's default assumption is often that someone or something must be responsible. However, nature routinely produces phenomena that surpass human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under conditions ranging from the interiors of massive stars to the near-absolute zero temperatures of interstellar space. The fact that we occasionally encounter natural processes or objects that surprise us is not evidence of artificial origin. It is evidence that our understanding of cosmic phenomena remains fundamentally incomplete. The media landscape surrounding astronomical discoveries also tends to amplify speculation about artificial origins. Headlines reading, "Scientists baffled by mysterious interstellar visitor," generate more clicks than "Researchers study unusual but natural comet." Regardless of which headline more accurately reflects the scientific consensus, this creates a feedback loop where public interest drives sensationalized coverage, which in turn fuels more speculation about exotic explanations. Social media exacerbates this effect by allowing unfiltered speculation to spread faster than careful scientific analysis. By the time astronomers have gathered sufficient data to characterize an object's properties and rule out artificial origins, alternative theories have already achieved viral status and become resistant to correction through factual information. The historical pattern is clear and consistent. Every unusual astronomical discovery, from pulsars to fast radio bursts, has initially faced speculation about possible artificial origins. In every instance, continued observation and analysis have revealed natural explanations that, while often more complex and fascinating than initially anticipated, require no involvement of extraterrestrial intelligence. This does not mean we should abandon the search for evidence of extraterrestrial technology. The universe almost certainly harbors other intelligent civilizations, and some of them might be capable of interstellar travel or communication. However, the detection of such civilizations will necessitate clear, unambiguous evidence of artificial origin. Coherent radio signals with informational content, objects displaying controlled motion inconsistent with natural forces, or structures that violate the laws of physics as we understand them. 3I Atlas displayed none of these characteristics. Its radio emissions, where detected, consisted entirely of natural thermal radiation and molecular line emissions typical of cometary outgassing. Its trajectory followed predictable gravitational mechanics, augmented by volatile sublimation. Its internal structure, as revealed by thermal modeling and photometric observations, was consistent with a loose aggregate of ice and rock, held together by weak gravitational and cohesive forces. Perhaps most tellingly, 3I Atlas was behaving exactly as we would expect from the debris of planetary formation around other stars. Theoretical models predict that every star system should eject significant quantities of small bodies during its formation and early evolution. These objects would wander through interstellar space for millions or billions of years before occasionally encountering other stellar systems, where they might be observed as interstellar visitors. The chemistry and physical properties of such objects should reflect the conditions in their parent systems: different stellar masses, different elemental abundances, different planetary configurations, different thermal histories. An authentic sample of another star system's debris should appear alien compared to solar system objects, while still adhering to the same fundamental laws of physics and chemistry that govern matter throughout the universe. In other words, 3I Atlas looked exactly like what it claimed to be: a natural product of planetary system formation around another star, carrying chemical signatures that reflect formation conditions different from those that produced our local solar system family. The fact that it seemed strange to human observers was not evidence of artificial origin, but rather confirmation that we inhabit a galaxy where conditions for planetary formation vary dramatically from system to system. As 3I Atlas continued its approach toward perihelion, the accumulated evidence consistently supported natural explanations for its unusual properties. But this raised an even more intriguing question than whether it might be artificial. Where exactly had this ancient wanderer spent the billions of years between its ejection from whatever star system created it and its recent arrival in our cosmic neighborhood? The answer to that question would require sophisticated modeling of galactic dynamics and stellar motions across geological timescales. However, preliminary attempts to trace 3I Atlas's trajectory backward through space and time were already yielding tantalizing clues about the object's origins and the remarkable journey that had brought it to our telescopes at precisely the right moment for detailed study. Part 9. Origins and Biography of 3I Atlas. Reconstructing the biography of an interstellar visitor requires retracing a journey that may have spanned longer than Earth has existed. 3I Atlas carries within its chemistry and trajectory the fossilized record of cosmic events that unfolded billions of years ago, when our galaxy was younger and the distribution of stars and heavy elements differed dramatically from today's configuration. The initial clues to the object's ancient origins emerge from kinematic analysis, mathematical modeling that attempts to trace its motion backward through space and time. Preliminary calculations by researchers at the European Southern Observatory suggest that 3I Atlas may have originated from the galactic thick disk, a population of stars that formed during the Milky Way's early evolution between 7 and 12 billion years ago. If these kinematic models prove correct, 3I Atlas would be older than our entire solar system. It would have been drifting through interstellar space since before the Sun coalesced from its parent molecular cloud, carrying chemical signatures from an era when star formation rates were higher and the galaxy's heavy element content was substantially different from today's values. The thick disk hypothesis gained support from the object's unusual chemistry. The celestial bodies inhabiting this ancient galactic region typically exhibit distinct compositional signatures, differing markedly from the more contemporary, flattened populations like our own solar neighborhood. The observed scarcity of iron and the pronounced presence of carbon compounds within 3I Atlas hint at its formation in proximity to a thick disk star, characterized by a non-standard metallicity and an unusual abundance of volatile elements. The pertinent question then arises: how does a minor celestial object dislodge itself from its stellar cradle and embark on an extended voyage through the interstellar void? Such an expulsion typically stems from gravitational engagements with colossal planets during the nascent, tumultuous stages of planetary system development. As these massive worlds shift their orbits, either inward or outward, driven by interactions with surrounding protoplanetary material, they can hurl smaller entities onto unbound trajectories, effectively banishing them from the system. Sophisticated computer simulations indicate that virtually every planetary system expels substantial quantities of material during its formation. For every unit of mass that remains gravitationally bound within planets, asteroids and comets, it's estimated that approximately 10 units are propelled into interstellar space via gravitational slingshot maneuvers. This suggests that our galaxy should teem with trillions of rogue fragments originating from billions of stellar nurseries, forming a vast diaspora of planetary detritus adrift between the stars. Once expelled from its original solar system, 3I Atlas would have commenced a solitary expedition through the near-perfect vacuum of interstellar space. The average density of matter in the interstellar medium hovers around a single atom per cubic centimeter, a vacuum far superior to any achievable in terrestrial laboratories. In such an environment, the object would have been largely shielded from external influences, preserved in a cosmic deep freeze at temperatures mere degrees above absolute zero. Nevertheless, this interstellar transit was not entirely devoid of incident. Recent analyses by specialists in galactic dynamics have pinpointed several close passes with other star systems during 3I Atlas's lengthy journey. Over the preceding 10 million years alone, the object appears to have traversed within 1 parsec, roughly equivalent to 3 light-years, of at least 6 distinct stars, with each encounter potentially subtly altering its course through minor gravitational nudges. The most impactful of these stellar interactions occurred approximately 4 million years ago when 3I Atlas passed within roughly 1 light-year of a red dwarf star situated in the constellation Cassiopeia. The gravitational pull exerted during this close approach would have been sufficient to cause a measurable deviation in the object's trajectory, potentially elucidating why its current path does not point back towards any apparent progenitor system within the galaxy's thick disk population. This observation prompts intriguing inquiries regarding the object's surface evolution during its interstellar peregrination. The relentless bombardment by cosmic rays over millennia would have gradually modified the chemical makeup of exposed ice and rock through radiolytic and nuclear spallation processes. High-energy particles originating from distant supernovae and other galactic cataclysms would have fractured chemical bonds, generated unusual isotopic ratios, and possibly synthesized novel molecular species not typically found in solar system materials. The extreme frigidity of interstellar space, generally around 3 Kelvin, would have maintained most volatile compounds in a solid state throughout its journey. However, intermittent passages through interstellar dust clouds or proximity to stellar radiation fields may have triggered episodic warming events, capable of sublimating surface layers and redepositing them in altered configurations. This phenomenon could account for some of the peculiar chemical signatures detected by contemporary telescopes. Perhaps most astonishingly, 3I Atlas has maintained its structural integrity over its billion-year voyage. Enduring thermal fluctuations, cosmic ray exposure, and occasional impacts from interstellar dust particles. This resilience suggests either an exceptionally robust composition or a continuous self-repair mechanism involving sublimation and redeposition, processes that gradually mend micrometeoroid damage and radiation-induced structural alterations. The object's arrival in our solar system marks the culmination of a journey that strains human comprehension. Consider the extraordinary precision in navigation required for 3I Atlas to reach us at the exact moment and along the precise trajectory for optimal observation by 21st century human telescopes. The object had to endure billions of years in the harsh interstellar environment, navigate the gravitational influences of dozens of stellar encounters, and arrive during the fleeting historical window when humanity possessed the technological capacity to detect and study it. This confluence of timing appears almost too serendipitous to be accidental. 3I Atlas approached perihelion just as our most advanced space telescopes were becoming operational, and our comprehension of interstellar chemistry had reached a level sophisticated enough to appreciate its significance. A few centuries earlier, it would likely have been dismissed as merely another indistinct celestial body. A few centuries later, it might have been detected, but not adequately characterized before vanishing back into the cosmic expanse. The history of 3I Atlas also illuminates the grander narrative of galactic evolution and the cyclical redistribution of planetary matter. Every heavy element within its composition was forged in the nuclear infernos of ancient stars and dispersed across space by supernova explosions. The carbon, oxygen, silicon, and trace metals constituting its structure represent the accumulated stellar alchemy from countless stellar generations that lived and perished long before our own solar system even coalesced. In a profound sense, 3I Atlas serves as an emissary from the ancient galaxy, bearing samples of planetary formation processes that transpired under conditions vastly different from those that shaped Earth and its celestial companions. The object's chemical makeup offers direct evidence of how volatile materials condense and evolve within stellar environments possessing varying masses, metallicities, and dynamical histories. However, perhaps the most awe-inspiring aspect of 3I Atlas's chronicle is what it reveals about the intrinsic interconnectedness of galactic-scale processes. This object originated as part of a planet-forming disk around another star, potentially in a region of the galaxy entirely remote from our own. Through an intricate chain of gravitational interactions, stellar movements, and cosmic contingencies, it ultimately found its way to our observatories, transporting information about its origins across immense distances and temporal scales. If the hypothesis of a thick disk origin is substantiated, 3I Atlas would be recognized as a fossil from the Milky Way's youth, an era when the galaxy was more actively engaged in star formation and the chemical composition of interstellar space differed substantially from current values. The study of this ancient wanderer could yield profound insights into galactic chemical evolution, early planetary formation mechanisms, and the distribution of volatile substances in the primordial galaxy. Yet despite the sophisticated modeling and chemical analyses undertaken, fundamental questions regarding 3I Atlas's origins remain unresolved. We are unable to definitively identify its parent star or the specific planetary system where it coalesced. The gravitational turbulence inherent in galactic evolution has obliterated most traces of its initial trajectory, leaving only statistical probabilities regarding its potential thick disk provenance. This uncertainty underscores the inherent difficulties of interstellar archaeology. Unlike terrestrial fossils embedded within datable geological strata, cosmic voyagers, such as 3I Atlas, bear no direct imprint of their temporal or spatial origins. Their narratives must be reconstructed through indirect evidence, including chemical composition, isotopic ratios, trajectory analysis, and statistical modeling of galactic dynamics. Nevertheless, these limitations do not diminish the significance of what 3I Atlas represents. Even without precise knowledge of its birthplace, we can be confident that it carries authentic samples from another world, formed under conditions distinct from those prevalent in our solar system. Each spectroscopic observation and chemical analysis yields new data concerning the diversity of planetary formation processes and the spectrum of environments where worlds can arise around other stars. As 3I Atlas continued its final approach towards perihelion in late October of the year 2025, astronomers were making preparations for the object's temporary obscuration by solar glare. The weeks immediately surrounding perihelion promised to be the most scientifically valuable period of the entire encounter, as maximal solar heating would induce heightened outgassing, potentially revealing subsurface materials preserved since the object's formation billions of years ago. However, the solar glare that would conceal 3I Atlas during its most active phase also injected an element of suspense into the unfolding narrative. Would the object survive its perihelion passage intact, or would thermal stresses fracture it into numerous fragments, akin to the fate of many comets before it? Upon its reappearance in telescopic view in December, would it continue to exhibit the same unusual chemistry and complex activity patterns that had rendered it so remarkable during its inbound trajectory? Answers to these questions would necessitate patience. In the interim, the September surge and the extraordinary characteristics of 3I Atlas were prompting unsettling contemplations about the nature of our cosmic vicinity and humanity's place within it. Were we witnessing a random convergence of unrelated events, or could more profound patterns be at play, linking the interstellar visitor to the unusual occurrences? Some researchers began to posit that the September events represented not merely a statistical coincidence, but the prelude to something far grander, a cosmic drama unfolding on scales that might dwarf human comprehension of celestial mechanics and galactic evolution. Part 10. Spectacular what-ifs, cosmic dominoes. The human imagination, when confronted with phenomena that transcend our everyday experience, tends to gravitate towards spectacular explanations. In the case of 3I Atlas and the September surge, speculation began to emerge regarding potential cascade effects. The notion that an interstellar visitor might somehow initiate a chain reaction of cosmic events capable of fundamentally altering our solar system's dynamics. Could 3I Atlas be gravitationally agitating the asteroid population, much like a cosmic spoon stirring ingredients in a celestial concoction? The mathematical evidence decisively refutes this romanticized concept, even at its estimated maximum mass of several trillion kilograms. 3I Atlas represents a mere gravitational minnow within the vast ocean of solar system dynamics. Its influence on near-Earth objects at distances of millions of kilometers would be utterly negligible compared to the overwhelming gravitational dominance of the Sun and planets. Newton's inverse square law is unforgiving in its mathematical precision. Gravitational effects diminish with the square of the distance, meaning 3I Atlas's capacity to influence other objects drops to essentially zero at the scales pertinent to the September encounters. To provide perspective, the gravitational pull between 3I Atlas and asteroid FA22 during their simultaneous presence in the inner solar system would be roughly equivalent to the gravitational attraction between two automobiles parked in neighboring cities. Yet the persistence of gravitational shepherding theories reveals something significant about human psychology and our relationship with cosmic phenomena. We instinctively seek causal connections between simultaneous events, even when the underlying physics renders such connections impossible. This propensity served our ancestors well in identifying cause and effect relationships in terrestrial environments, but it can lead us astray when applied to astronomical phenomena operating on scales that dwarf human experience. More exotic cascade scenarios involve potential links between 3I Atlas and solar activity. Could an interstellar visitor somehow provoke increased solar flaring or coronal mass ejections that might impact space weather around Earth? This idea taps into legitimate concerns regarding solar-terrestrial interactions and the vulnerability of modern technological civilization to geomagnetic storms. However, the physics governing solar dynamics operate on energy scales that render comet-solar interactions essentially inconsequential. The Sun expends approximately 3.8 times 10 to the power of 26 watts of energy continuously. More power in 1 second than human civilization has consumed throughout all of recorded history. The gravitational and electromagnetic influence of a small interstellar comet at distances exceeding 100 million kilometers would be completely overwhelmed by the far greater forces driving solar variability. Solar activity follows well-documented cycles related to the Sun's internal magnetic dynamo, not the presence or absence of minor visitors in the outer reaches of the solar system. Correlations between comet appearances and solar events occasionally occur purely by chance, but these coincidences represent statistical noise rather than causal relationships. The meteor shower scenario presents another tempting yet ultimately unsupported speculation. Could 3I Atlas be trailing a debris stream that might produce spectacular meteor displays as Earth passes through the material? This notion gains superficial plausibility from the fact that many annual meteor showers result from Earth encountering debris streams left behind by comets. However, interstellar meteor streams face fundamental physics challenges that render them virtually undetectable from Earth. The debris ejected from 3I Atlas possesses the same hyperbolic velocity as the parent object, meaning any particles it sheds will also escape the solar system rather than settling into stable orbits that could intersect Earth's path. By the time our planet reaches the region through which 3I Atlas passed, any ejected material will have dispersed across volumes of space so vast that the particle density becomes negligible. Furthermore, the high relative velocities involved in interstellar encounters mean that any debris particles that did somehow intersect Earth would impact our atmosphere at speeds exceeding 70 kilometers per second, considerably faster than typical solar system meteors. Such high-velocity impacts would produce brief, brilliant flashes rather than the prolonged streaks characteristic of normal meteor showers. The fragmentation fantasy represents yet another attempt to uncover hidden connections between 3I Atlas and the September asteroid encounters. Could FA-22 and the other near-Earth objects be fragments of the interstellar visitor, broken off during a prior passage through the inner solar system and now following independent orbits that bring them back into Earth's vicinity? This scenario faces insurmountable challenges related to orbital mechanics and chemical composition. True fragments from 3I Atlas would retain hyperbolic trajectories and interstellar chemistry analogous to the parent object. The September asteroids exhibit neither characteristic. Their elliptical orbits and typical carbonaceous or silicate compositions indicate conventional solar system origins, devoid of any connection to interstellar material. Perhaps the most persistent cascade speculation involves institutional secrecy. The idea that governmental agencies might be withholding evidence of more dramatic effects or discoveries related to 3I Atlas. This theory draws upon legitimate concerns about transparency in space surveillance and the potential for classified military implications arising from asteroid detection capabilities. However, the reality of modern astronomical practice argues strongly against large-scale cover-up scenarios. The global network of professional and amateur astronomers operates on principles of open data sharing and rapid dissemination of discoveries. Major observatories publicly announce their observation schedules and target lists. Orbital elements for newly discovered objects appear in international databases within days of confirmation. The incentive structure of academic astronomy also militates against secrecy. Career advancement hinges on publishing significant discoveries in peer-reviewed journals and presenting findings at international conferences. A conspiracy to suppress information concerning 3I Atlas would necessitate the coordinated efforts of thousands of researchers across dozens of nations, a logistical impossibility given the inherently competitive nature of scientific research. More fundamentally, there is simply no credible evidence of hidden effects or concealed discoveries associated with 3I Atlas. Every aspect of the object's behavior, chemistry, and trajectory has been consistent with natural phenomena, albeit natural phenomena at the extreme end of previously observed ranges. Yet even as rational analysis dismisses the more spectacular cascade scenarios, one genuine what-if scenario warrants serious consideration. The possibility that we are entering an era of dramatically increased interstellar visitor detection. The Vera C. Rubin Observatory's unprecedented survey capabilities, coupled with improving space-based infrared telescopes and enhanced international coordination, could reveal that objects like 3I Atlas are far more prevalent than previously presumed. Current estimates suggest that the Oort cloud and similar structures around other stars should eject approximately one interstellar object per year that becomes detectable from Earth using existing survey capabilities. However, these estimates are subject to immense uncertainties, based on limited observational data from just 3 confirmed interstellar visitors. If the actual rate proves to be higher, perhaps 10 or 20 detectable interstellar objects per year, the late 2020s could witness a revolution in our understanding of galactic-scale material exchange. Instead of viewing interstellar visitors as rare cosmic curiosities, we might discover that our solar system is constantly bathed in debris from thousands of other planetary systems. This scenario would transform interstellar archaeology from a speculative science based on individual exotic objects into a systematic survey discipline capable of characterizing the chemical and physical properties of planetary formation across the galaxy. We could begin mapping the distribution of different stellar metallicities, volatile inventories, and planetary architectures by studying the debris streams that deliver samples from distant worlds directly to our telescopes. Such a revelation would represent perhaps the most profound shift in cosmic perspective since the Copernican revolution. Instead of viewing Earth and its solar system companions as isolated products of local stellar evolution, we would recognize ourselves as participants in a galaxy-wide ecosystem where material constantly flows between stellar systems across vast distances and temporal scales. The September surge, viewed from this perspective, might represent not an anomalous clustering of unrelated events, but our initial glimpse into the true level of activity within our cosmic neighborhood. As detection capabilities advance and survey coverage expands, what currently appears to be unusual activity might prove to be the norm for a galaxy containing 400 billion stars, constantly exchanging debris through gravitational interactions and stellar encounters. But before we can assess these broader implications, we must navigate the immediate challenge of 3I Atlas's perihelion passage and its subsequent reemergence from solar glare. The object's behavior during its closest approach to the Sun would provide critical data concerning the survivability of interstellar comets and the preservation of ancient chemical signatures under extreme thermal processing. The stakes involved transcend mere scientific curiosity. Should the enigmatic 3I Atlas shatter during its close solar passage, humanity might forfeit the chance to examine pristine interstellar matter for potentially centuries, awaiting another such cosmic traveler with opportune observational alignment. Conversely, if it endures, the object's reappearance in December could offer an unprecedented, detailed examination of genuine extraterrestrial material, a feat never before achieved by our scientific endeavors. Section 11. Observing Opportunities, late 2025 to 2026. The intricate celestial ballet of late 2025 was reaching its crescendo as 3I Atlas drew nearer to its fated encounter with the Sun. October 31st was the projected date for its closest approach, the moment this ancient cosmic wanderer would traverse its nearest point to our star, following a journey possibly spanning longer than Earth's own existence. However, this pivotal moment would transpire beyond the reach of direct human observation, obscured by the brilliant effulgence of our solar neighbor. For scientists across the globe, this perihelion period presented both the peak of scientific potential and the most vexing observational hurdle. This was the time when the intense solar radiation would catalyze the highest levels of volatile ice vaporization, potentially unveiling materials preserved since the object's inception billions of years ago. Chemical compounds, locked in solid form during their protracted interstellar voyage, would finally transform into gas, revealing their spectral signatures to any telescope equipped to capture them. Yet the very solar energy that promised to unlock 3I Atlas's deepest secrets would render it virtually imperceptible from Earth. The object's trajectory would bring it to within approximately 0.44 astronomical units of the Sun, a distance of about 60 million kilometers, closer than Mercury orbits. From our vantage point, this placed 3I Atlas less than 10 degrees from the solar disk, lost within the dazzling twilight that renders precise astronomical observation impossible. This imposed observational hiatus created an intriguing enigma. Would 3I Atlas emerge from perihelion intact, rejoining us in December as a singular entity exhibiting heightened activity due to fresh, volatile release? Or would the thermal pressures fracture its internal structure, breaking it into multiple pieces that would form an expanding cloud of debris, visible as distinct cometary bodies? The question of survival held implications far beyond mere academic interest. Intact survival would imply that interstellar objects possess sufficient structural fortitude to retain ancient chemical imprints, even under extreme solar heating. Fragmentation, while visually spectacular, might disperse precisely the materials that rendered 3I Atlas scientifically invaluable, transforming a pristine sample from another star system into a collection of processed debris. Historical precedent offered little clarity. Most comets within our solar system that fragment during close solar approaches originate from the Oort cloud, experiencing significant solar radiation for the first time after eons in frigid storage. 3I Atlas, in contrast, was a veteran survivor, having already demonstrated remarkable structural resilience throughout its billion-year sojourn through interstellar space. The cosmic irony was profound. After traversing unimaginable distances through space and time to reach our solar system, 3I, Atlas would experience its most dynamic and revealing phase hidden behind the very star driving its remarkable transformation. It was akin to witnessing a concert where the main performer vanishes behind a curtain during their most significant piece. Nevertheless, astronomical patience often yields substantial rewards. Earth's orbital movement around the Sun gradually improves the viewing geometry for objects passing close to our star. By early December, 3I Atlas would begin to emerge from the solar glare, entering an optimal observational position. The object's closest approach to Earth was predicted for mid-December at a distance of approximately 1.8 astronomical units, roughly 270 million kilometers. While this distance might seem considerable by terrestrial standards, it represented ideal conditions for detailed spectroscopic analysis. Close enough for major telescopes to gather ample light, yet distant enough to avoid interference from Earth's own thermal radiation, and positioned in the pre-dawn sky where background light pollution would be minimal. This December observation window would likely constitute the most significant opportunity for studying intact interstellar material that human science might encounter for decades, if not centuries. Unlike the brief passage and rapid departure of Oumuamua, 3I Atlas's trajectory and timing would keep it within the reach of major observatories well into 2026, affording months of continuous observation across various wavelengths. Meanwhile, other celestial participants from the September Cosmic Ensemble were preparing for their own observational moments. Comet 2025. R2 Swan, whose brightness had steadily increased throughout autumn, faced its own survival test as it neared perihelion in early November, with the potential for fragmentation under solar heating. Should Swan persevere, it promised breathtaking naked-eye viewing for observers in the northern hemisphere. The comet's visibility was diminishing as its path drew it deeper into the evening twilight, but seasoned comet enthusiasts reported possible naked-eye detection under dark, rural skies. Binoculars revealed a distinct greenish coma and a developing tail structure extending away from the Sun, classic indicators of active volatile sublimation. Whether this spectacle would persist or culminate in catastrophic fragmentation remained to be determined. Asteroid 9942. Apophis continued its relentless approach toward its April 2029 rendezvous, which would bring it closer to Earth than our geostationary satellites. Although still 3.5 years away, ground-based telescopes had already commenced extensive characterization campaigns to map the asteroid's surface properties, rotational state, and internal structure before the close flyby potentially altered these attributes. NASA's OSIRIS-Apophis spacecraft, en route to rendezvous with Apophis after its Earth encounter, was conducting scheduled check-ins and navigation adjustments during its multi-year cruise phase. The spacecraft was slated to reach Apophis in June 2029, providing close-up observations of how the gravitational interaction with Earth had affected the asteroid's physical characteristics. However, the most significant enhancement to our cosmic surveillance capabilities was still ramping up its operations. The Vera C. Rubin Observatory's initial images had demonstrated an unprecedented capacity for discovering and tracking near-Earth objects. Nevertheless, the facility was still in its commissioning phase during the autumn of 2025. Once fully operational, the Rubin Observatory would survey the entire accessible sky every few nights, offering near real-time monitoring of celestial traffic in our local cosmic vicinity. This intensified observation cadence would revolutionize asteroid detection and tracking, potentially revealing that the September surge was not an isolated event, but rather a representative sample of the true activity level in near-Earth space. Previous surveys, with much longer intervals between observations, might have overlooked numerous objects or failed to identify clustering patterns that would become evident under continuous surveillance. The space-based component of our detection network was also undergoing significant upgrades. NASA's Near-Earth Object Surveyor, scheduled for launch in September 2027, would deploy an infrared telescope specifically designed for asteroid detection. Operating from an orbital position trailing Earth, NEO Surveyor would be capable of detecting objects approaching from the direction of the Sun, which are currently invisible to ground-based surveys. This capability would finally close the detection gap that allowed the Chelyabinsk impactor to arrive entirely unnoticed in 2013. Once operational, NEO Surveyor is expected to provide advance warning of incoming objects regardless of their approach vector, eliminating the solar blind spot that constitutes our most significant vulnerability in planetary defense. For amateur astronomers and citizen scientists, the late 2025 period presented multiple avenues for valuable contributions to ongoing research. Comet Swan remained within reach of modest telescopes and even sophisticated cameras, enabling dedicated observers to document changes in tail structure, brightness fluctuations, and potential fragmentation events. 3I, Atlas's December reappearance would initially favor observers in the southern hemisphere, but its swift movement across the sky would eventually bring it within range of northern observers as well. While the comet would be too faint for visual observation without significant telescopic aid, skilled astrophotographers might be able to capture images revealing coma structure and tail development. More crucially, the coordinated observation of these multiple celestial bodies provided invaluable experience in international scientific collaboration and data sharing. The methodologies and protocols developed for tracking 3I Atlas and characterizing the September surge would be directly transferable to future planetary defense scenarios involving potentially hazardous asteroids with short warning periods. The observational challenges of late 2025 also underscored the importance of redundancy and international coordination in astronomical surveys. No single telescope or survey system can provide complete coverage of all potential approach, vectors, and object types. Only through synchronized efforts between ground-based and space-based facilities, utilizing multiple wavelength ranges and observation cadences, can we achieve comprehensive awareness of our cosmic neighborhood. As autumn transitioned into winter and 3I Atlas prepared for its obscured solar encounter, the global astronomical community was mobilizing resources for what might become the most intensive characterization of interstellar material ever undertaken. The implications extend far beyond academic curiosity. Data gathered during the December observation window could offer crucial insights into planetary formation processes, galactic chemical evolution, and the frequency of interstellar material exchange between star systems. But first, 3I Atlas had to survive its appointed meeting with our Sun. The answer to that question would remain concealed until December, when telescopes worldwide would turn towards the pre-dawn sky to ascertain whether ancient chemistry from another star system had endured one final trial in its billion-year journey to reach human science. Part 12. Envisioning futures, potentialities, and speculative trajectories. The confluence of enhanced detection capabilities, improved deflection technologies, and growing international cooperation in the late 2020s is setting the stage for a multitude of potential futures in humanity's interaction with cosmic hazards. The September surge and the 3I Atlas encounter offer glimpses of what these futures might entail, ranging from triumphant command over our celestial environment to sobering acknowledgments of our persistent vulnerability. In the most optimistic scenario, the technological and institutional frameworks established during the 2020s mature into a robust planetary defense system that effectively eradicates asteroid impact risks while profoundly advancing our understanding of the broader galactic setting. The capabilities of the Vera C. Rubin Observatory, coupled with space-based infrared detection from NEO Surveyor and analogous systems, create a comprehensive awareness of incoming objects with decades or centuries of advance notice. This extended lead time transforms deflection from desperate last-minute interventions into routine management of celestial traffic. Gentle adjustments applied years in advance divert potentially dangerous objects onto safe trajectories using proven kinetic impact techniques, refined through multiple missions akin to the DART experiment. The process becomes so dependable and predictable that asteroid deflection joins earthquake prediction and hurricane tracking as accepted tools for mitigating natural disasters. Under this scenario, Comet Swan successfully navigates its 2025 perihelion passage and provides spectacular naked-eye viewing throughout the Northern Hemisphere's winter, inspiring a new generation of amateur astronomers and science enthusiasts. 3I Atlas emerges intact from its solar encounter, yielding unprecedented insights into interstellar chemistry and the processes of galactic material exchange. The detailed characterization of 3I Atlas establishes interstellar archaeology as a significant scientific discipline. Improved survey systems detect dozens of additional interstellar visitors throughout the late 2020s, each bearing unique chemical signatures that illuminate different facets of planetary formation around other stars. By the early 2030s, the systematic comparison of interstellar debris yields the first comprehensive survey of planetary chemistry across diverse galactic environments. This scientific bounty spurs technological advancements in spectroscopy, precision astrometry, and coordinated multi-telescope observations. The same capabilities prove invaluable for characterizing potentially hazardous asteroids, enabling precise determination of composition, structure, and deflection requirements well in advance of any actual threats. International cooperation flourishes under the pressure of shared cosmic challenges. The protocols developed for coordinating observations of 3I Atlas evolve into standardized procedures for managing any anomalous or threatening objects. Regular drills and training programs maintain readiness while fostering confidence in global response capabilities. Public engagement with astronomy and space science reaches unprecedented levels as people worldwide follow the ongoing discoveries and characterization efforts. Educational initiatives leverage this interest to enhance scientific literacy and rational decision-making skills across diverse populations. The combination of genuine cosmic threats and effective technological responses provides compelling evidence for the value of scientific research and international cooperation. However, alternative scenarios present more challenging possibilities. The moderate pathway acknowledges that improved detection and deflection capabilities will inevitably face real tests as the catalog of potentially hazardous objects expands. Current surveys have identified most kilometer-plus asteroids capable of causing global catastrophe, but the inventory of city-killer-sized objects in the 100 to 300-meter range remains incomplete. Statistical projections suggest that one or more objects in this size range will eventually approach Earth with insufficient warning time for gentle deflection maneuvers. These scenarios would necessitate more aggressive intervention techniques, potentially including nuclear explosive devices, which carry significant technical and political risks. The first such encounter might involve an object discovered only months or weeks before potential impact, forcing rapid decisions about deflection strategies under immense time pressure and public scrutiny. Success would validate planetary defense investments and likely trigger expanded funding for detection and deflection capabilities. Failure could result in regional devastation and fundamental questions about humanity's capacity to protect itself from cosmic threats. Even partial success scenarios carry significant implications. A deflection attempt that successfully averts global catastrophe but fails to eliminate all impact risk might scatter debris across populated areas, creating multiple smaller impact sites instead of a single large crater. Public perception of such outcomes could shift from viewing planetary defense as heroic protection to considering it as dangerous interference with natural processes. Ocean impacts present particularly complex challenges for both deflection strategy and public communication. The majority of Earth's surface is covered by water, making ocean impacts statistically more probable than land impacts for randomly arriving asteroids. However, tsunami generation from ocean impacts remains poorly understood, with considerable uncertainties in current modeling efforts. A 200-meter asteroid striking deep ocean could potentially generate 10-meter waves that remain dangerous across entire ocean basins. Coastal cities from Boston to Barcelona could face devastating tsunami impacts hours after a mid-Atlantic collision. The warning time provided by successful detection might suffice for evacuation efforts, but the economic and social disruption would be immense even without direct casualties. These scenarios highlight the importance of accurate risk communication and realistic public expectations regarding planetary defense capabilities. Our current technology can likely manage most threats given adequate advance warning. However, late discovery scenarios or unusually large objects could overwhelm existing deflection capabilities. The worst-case scenarios, while statistically improbable on human timescales, represent existential challenges that current technology cannot effectively address. A long-period comet from the Oort cloud could arrive with only months or years of advance notice, possessing enough kinetic energy to threaten human civilization, irrespective of deflection attempts. Such objects with diameters potentially exceeding 10 kilometers would require deflection energies far beyond anything achievable through kinetic impact techniques. Nuclear explosive deflection might be theoretically feasible, but the necessary technology development, international coordination, and deployment timelines could easily exceed available warning periods. These extreme scenarios serve as reminders that planetary defense offers protection against most threats, not all threats, akin to earthquake-resistant building codes or hurricane tracking systems. Defensive measures can significantly reduce risks without eliminating them entirely. The objective is not absolute security, an unattainable standard, but rather reasonable protection against reasonably probable threats. Population psychology and social dynamics introduce additional complications across all scenarios. Public reaction to asteroid threats depends heavily on risk communication strategies, media coverage patterns, and existing levels of trust in scientific and governmental institutions. Accurate information disseminated by credible sources can maintain social stability during crisis situations. Sensationalized reporting or conspiracy theories can undermine response effectiveness even when technical capabilities are adequate. The September surge provided valuable experience in managing public communication regarding cosmic threats, but actual impact scenarios would involve much higher stakes and more intense media scrutiny. Social media amplification of both accurate information and misinformation could significantly complicate crisis management efforts. Economic implications also vary dramatically across different scenarios. Successful deflection of major threat could generate immense public support for continued investment in planetary defense capabilities. Failed or partially successful interventions might prompt more cautious approaches, emphasizing evacuation and damage mitigation over active deflection attempts. The commercial space industry's growing involvement in asteroid-related activities introduces market dynamics that could either support or complicate planetary defense efforts. Private companies motivated by asteroid mining profits might develop characterization and rendezvous capabilities that serve dual purposes for both resource extraction and deflection missions. Commercial imperatives do not consistently align with the demands of planetary defense. An asteroid presenting a significant hazard could also hold valuable mineral deposits, leading to competing interests between resource extraction corporations and missions focused on planetary protection. Such discrepancies would necessitate robust regulatory frameworks to ensure a balance between commercial aspirations and the imperative of public safety. International politics emerge as a potentially the most volatile element in future planetary defense considerations. While existing collaborative structures function effectively during ordinary operations, crises involving potential celestial impacts might incite more competitive nationalistic responses. Nations might opt for independent measures to avert threats rather than engaging in coordinated international efforts, potentially resulting in conflicting or counterproductive actions. The evolutionary path of technological advancement will also shape the likelihood of various scenarios. Significant breakthroughs in areas such as fusion power, propulsion systems, artificial intelligence, or material science could vastly enhance our defensive capabilities and extend the duration of effective warning periods. Conversely, a lack of technological progress or diminished funding for space-based observation networks could leave humanity vulnerable to threats that current projections assume we will be equipped to address. Concerns like climate change and other global challenges vie for the same financial and political capital required for planetary defense initiatives. Public and governmental attention possess finite capacity, and threats posed by asteroids, which may seem abstract or distant, could be deprioritized in favor of more immediate issues such as economic disparities, environmental deterioration, or international conflicts. Nevertheless, the universal perspective offered by celestial bodies like 3I Atlas presents unparalleled opportunities to surmount earthly divisions and concentrate on shared human concerns. The realization that our planet exists within a dynamic galactic environment, populated by both potential hazards and opportunities, could foster cooperation in ways that challenges confined to Earth cannot achieve. As we approach what could be a period of transformative advancements in our capacity to monitor and manage cosmic dangers, the future trajectories that materialize will depend as much on our societal and political decisions as on our technological prowess. The event in September and the close encounter with 3I Atlas serve as both an encouragement and a caution regarding what lies ahead in humanity's relationship with the broader cosmic expanse. However, before any of these long-term prospects can materialize, we must first ascertain what 3I Atlas reveals upon its reappearance from its solar concealment in December. The chemical indicators and physical attributes recorded during that critical observation period may offer our initial detailed insight into genuine matter originating from another star system, and our first true comprehension of what it signifies to be inhabitants of a galaxy where worlds continuously exchange their most prized substances across the immense gulfs separating stars. Part 13. Conclusion. A cosmic perspective. As winter envelops the northern hemisphere and 3I Atlas prepares for its re-emergence from the sun's glare in December, we find ourselves at a pivotal moment in humanity's connection with the cosmos. The occurrences of September 2025, ranging from the close passage of FA22 to the increased brightness of Swan, and the identification of our third confirmed visitor from beyond our solar system, have provided us with something far more valuable than mere scientific data or validation of planetary defense strategies. They have bestowed upon us a new lens through which to perceive our position in the universe. For the majority of human history, the night sky appeared unchanging and predictable. Stars traced eternal arcs across the heavens, planets followed predetermined routes, and the infrequent appearance of a comet or a shooting star served as a fleeting reminder that space was not entirely devoid of activity. This worldview cultivated a sense of cosmic solitude. Earth and its inhabitants seemed to be unique products of localized stellar processes, fundamentally separated from the remainder of the galaxy by distances and timescales that defied comprehension. The September surge irrevocably shattered this illusion of isolation. We discovered that our solar system is not a tranquil, out-of-the-way locale on the fringes of cosmic activity, but rather a bustling nexus where ancient voyagers from distant realms frequently pass through, bearing dispatches from their origins. 3I Atlas alone represents a tangible link to stellar phenomena that transpired billions of years ago in parts of the galaxy we may never reach with spacecraft. This signifies more than simply a scientific disclosure. It represents a fundamental alteration in cosmic perception, akin to the Copernican revolution or the revelation of the universe's expansion. We are not isolated outcomes of a singular star system, but active participants in galactic-scale processes that have facilitated the exchange of matter and information between worlds for a duration exceeding Earth's existence. The preserved chemical signatures within 3I Atlas's ancient composition contain vital information regarding stellar nucleosynthesis rates, conditions conducive to planetary formation, and volatile chemistry in environments that predated the sun's illumination. Each spectroscopic observation offers a direct sampling of the processes that shaped the galaxy during its nascent stages, when star formation was more prolific and the distribution of heavier elements was markedly different. However, perhaps most significantly, the September events have underscored our present possession of the technological capacity to identify, examine, and potentially engage with this galactic system of material transference. The same detection arrays that tracked FA22's approach and will monitor the 2029 flyby of Apophis are also capable of identifying and characterizing interstellar visitors like 3I Atlas with sufficient accuracy to extract detailed scientific insights. We have progressed from being passive observers of cosmic events to active participants in interstellar archaeology. Every new survey telescope brought online, every enhanced spectroscopic technique developed, and every international cooperation agreement established brings us closer to a comprehensive understanding of our galactic environs and our place within it. This transition carries profound implications that extend well beyond the realms of astronomy and planetary defense. The infrastructure necessary for monitoring cosmic threats and studying interstellar visitors, precision detection systems, rapid response capabilities, and international coordination mechanisms provides a model for addressing other global challenges that transcend national borders. Climate change, pandemic preparedness, resource management, and environmental stewardship all necessitate comparable combinations of scientific understanding, technological aptitude, and international collaboration. The insights gained from tracking asteroids and characterizing comets could prove equally valuable for monitoring greenhouse gas concentrations, forecasting disease outbreaks, or managing shared oceanic and atmospheric resources. More fundamentally, the cosmic perspective fostered by awareness of interstellar visitors, such as 3I Atlas, offers an antidote to the insular thinking that frequently hinders cooperation on global matters. When we recognize that Earth is situated within a dynamic galactic ecosystem, where matter continuously flows between stellar systems across vast distances and timescales, terrestrial distinctions based on nationality, ideology, or economic systems begin to appear less significant. We are all fellow travelers on this same small planet, navigating its course through a galaxy teeming with ancient debris from countless other worlds. The carbon atoms in our bodies were forged in stellar furnaces that extinguished themselves before our sun even began to form. The water we drink may have arrived via comets from the distant outer reaches of our solar system. The air we inhale comprises elements that have traversed interstellar space for longer than complex life has existed on Earth. This realization transforms environmental protection and social cooperation from abstract moral obligations into practical imperatives for cosmic citizenship. We cannot afford to squander the rare and precious conditions that permit the flourishing of complex chemistry and biological evolution on planetary surfaces. Nor can we afford to fragment our response capabilities through short-sighted competition when confronted with challenges that operate on a galactic scale. The September surge has also illuminated the extent of our present ignorance regarding our cosmic neighborhood and the processes that govern it. Current models suggest that interstellar visitors should be relatively infrequent, perhaps one observable object every few years under optimal observational conditions. However, if 3I Atlas represents a typical rather than an exceptional level of activity, our estimations could be off by orders of magnitude. The Vera C. Rubin Observatory and other next-generation survey systems could reveal that dozens or even hundreds of interstellar objects traverse our solar system annually, the majority of which are too small or faint to be detected with present technology. This would revolutionize our understanding of galactic material exchange rates and the frequency of information transfer between stellar systems. Such discoveries would also prompt profound inquiries into the prevalence of complex chemistry and potentially biological processes throughout the galaxy. If interstellar space is replete with organic compounds and volatile materials that originated from diverse planetary environments, then the fundamental ingredients for life might be distributed far more widely than we currently comprehend. Every comet that enters our solar system, whether originating from the local Oort cloud or distant interstellar space, carries with it samples of the chemical conditions present during its formation. These natural laboratories provide direct access to processes and environments that remain beyond the reach of our most ambitious spacecraft missions. Nevertheless, studying these cosmic couriers necessitates sustained investment in comprehensive detection, tracking, and characterization capabilities, the very tools that facilitated the September discoveries. The technologies and institutional frameworks that enabled us to identify 3I Atlas as an interstellar visitor and ensure FA-22's safe passage represent decades of scientific advancement and international collaboration. These capabilities are not self-sustaining. They require continuous funding, technological upgrades, and political backing from governments and institutions worldwide. The extended intervals between significant impact threats or remarkable interstellar visitors can create a temptation to reduce investments in planetary defense and cosmic surveillance systems. Such a course of action would constitute a grave error. The September surge has demonstrated that our cosmic environment is far more active and interconnected than we previously appreciated. We are finally developing the observational and analytical instruments required to comprehend our place within a cosmos that has been operating for billions of years. The forthcoming decades hold the potential for transformative breakthroughs in our understanding of planetary formation, stellar evolution, and galactic chemical evolution, derived from the direct examination of interstellar materials delivered to our telescopes by natural cosmic processes. This can only be achieved, however, if we maintain and expand the capabilities that made these discoveries possible. The choice before us is unequivocal. We can embrace our role as cosmic citizens, investing in the technologies and institutions essential for monitoring and understanding our galactic environment while simultaneously safeguarding our planet from celestial threats. Alternatively, we can retreat into terrestrial provincialism, abandoning the cosmic perspective precisely as we begin to glimpse the true complexity and wonder of the universe we inhabit. The September surge and the encounter with 3I Atlas offer a compelling argument for the former path. We have been granted extraordinary opportunities to examine authentic samples from other star systems while simultaneously demonstrating our evolving capacity to protect Earth from cosmic dangers. These achievements signify the commencement of humanity's transition from a species confined to its planet to active participants in galactic-scale phenomena. Yet this transition will only prove successful if we sustain the curiosity, cooperation, and dedication to scientific understanding that made it possible. The cosmos has bestowed remarkable gifts upon our telescopes and detection networks. Whether we prove ourselves worthy of these gifts will be determined by the choices we make in the ensuing months and years. As 3I Atlas prepares to emerge from behind the sun's glare, carrying chemical signatures from another star system and a distinct era of galactic evolution, we stand prepared to receive its messages concerning planetary formation processes and the cosmic exchange of materials, which we could never study through any other means. What we glean from this ancient wanderer may fundamentally alter our understanding of how planets form around distant stars, how life's essential components are disseminated throughout the galaxy, and what it truly signifies to be cosmic citizens in a universe where 400 billion stars perpetually exchange their most precious substances across the immense voids of interstellar space. The September surge was merely the preamble. The true adventure in cosmic archaeology and interstellar comprehension lies ahead, awaiting our development of the wisdom and collaborative spirit necessary to decipher the messages that ancient voyagers like 3I Atlas convey across the dark expanses between worlds.